Okay, well, welcome to my presentation and quest to get SocketCAN working into NuttX. So first, let's talk something about NXP. Ian didn't do enough about it, but let's just start about some basics. So I'm working at the mobile robotics team at NXP. Previously, it was a small drone teams. Now we're mostly focusing on mobile robotics, on drones, on rovers, other vehicles, and we're applying different products, and we're using NuttX and PX4 for that. Mainly, I'm also focusing on automotive functional safety. So we're looking at to get our automotive product lines into these rovers, and in there we're also using NuttX for that. So that's our S32 line. Just a reminder: we don't build drones; we build reference designs. So our main goal is to come up with a reference design, getting software to work, and showcase the capabilities of our hardware. So the outline for today. First, I want to just shortly introduce what CAN bus is. Then I want to highlight the existing CAN bus subsystem in NuttX. Then I want to showcase the SocketCAN in NuttX. I have a demo, and I want to have a small talk about where do I use NuttX and SocketCAN for. So what is CAN bus? CAN bus is a controller area network. It allows microcontrollers to communicate to other microcontrollers. So instead of a point-to-point connection, you have a bus topology. So you have a single twisted pair of wire, which is shared between different microcontrollers, and they share this bus, but they can communicate to each other. It's a broadcast mechanism, so if one microcontroller communicates, each microcontroller receives it. The communication goes through so-called CAN frames, which has an identifier. This identifier also is the priority and also enforces real-time behavior, which is nice for control technology. That's why it's also used a lot in cars. And last, you have a payload which can differ between 1 byte to 64 bytes, depending you're using CAN or CAN-FD. So the existing CAN subsystem in NuttX. So the existing CAN subsystem is based on a existing hardware CAN driver. In NuttX, it's a POSIX-based operating system. So the idea is that you have files to communicate, and they made a character device driver to communicate over CAN. So you have to open your character device, and you can use ioctls to configuration. You get your data in through. So the things we really didn't like about this is that it's not really a portable API. It's still a nice and clean and simple API, but it's NuttX specific. And we want to look at what's a nice standardized API for industry. And we also had some other use cases for real-time behavior, multi-user. And looking at this picture, we felt it really is in a better place if you put something like this in the networking stack. So we looked at the SocketCAN. So SocketCAN is initially implemented in the Linux kernel by the Volkswagen Research Group. They provide a multi-user system, also a hardware-independent socket-based API to do communication. So what has changed is that the SocketCAN goes through the Berkeley sockets. We add a Berkeley socket CAN protocol family. So the nice thing is that NuttX already has this socket interface. We already have a socket API, so we only have to extend it with the CAN protocol family. And the main idea is that if we finally have this SocketCAN into NuttX, we can easily integrate existing applications that are running on Linux, but you also nowadays have QNX and other commercial operating systems that also have a POSIX interface and also support this SocketCAN. So the idea is that you can easily port high-level protocols, but also just any other POSIX compatible SocketCAN application to NuttX. So what's our test vehicle? So internally we have this, well, it just got released in July. So we have this reference design from this S32K board. So the great part about this S32K, it already runs in NuttX. We already integrated in NuttX. We have two CAN controllers. We have classical CAN support. We have CAN FD support. So this is the high bitrate support for CAN. And it's a nice test bed to test this SocketCAN interface. So the main goal initially is to extend the existing protocol family where we add the the CAN to it, and we have to write a S32K FlexCAN driver, and we want to, of course, showcase some demo apps. So adding the CAN protocol stack. So thanks to Gregory Nutt first. So for me, I was pretty new into whole the networking side. So he created the initial steps for me. And eventually from there, it was pretty easily. I would say the network part is not super documented in NuttX, but if you look at the simplicity and how it works, and also mainly looked at the net packets, so these are raw packets over Ethernet, it's nice, it's easy to implement. So into the socket side of NuttX, we added the CAN side to NuttX. Yes. And eventually we wrote our own driver for hardware for our S32K chip. So our FlexCAN driver, so it's based on our Ethernet driver because in essence, the CAN driver is now as the same as an Ethernet driver, so it's just a network device. So most of the interfaces are the same. Unfortunately, I ran into one small problem, is that the original Ethernet driver uses the NuttX work queue to process packets. So an interrupt comes in, and we set up a work queue that can process the data. Unfortunately for me, the problem is that in CAN you have very small packets. They take less time, and they have to process immediately because inside a CAN controller you have just a certain amount of buffering. They call them mailboxes, and if they're not being emptied, we have an overflow. We miss out on CAN frames. So what you see here is you see data coming in. We have an interrupt, and we see some process time, and it's not ideally being scheduled, and eventually we cannot keep up and we lose data. So the solution for that, well, you can think about why not process this frame directly into an interrupt. Well, fortunately, this doesn't work because we just moved the whole CAN layer to the network stack, and the network has this network lock, so we have to synchronize on something. And initially, you did it through this work queue where you schedule a work queue and you wait for your lock and you process your data. And that was not possible. And the solution for that was that we just try to lock. So if we can get the semaphore, we take it and we put the frame in the socket. If we don't get it, NuttX already has this mechanism where you can store this frame in the read ahead buffer. And as a result, as you can see, is that processing is now just on time, and we don't have our receive buffer overflow. So it was a nasty problem to tackle, but eventually we got it. So SocketCAN in real time. So in our use case, we want to implement UAV CAN on top of SocketCAN, and we needed some extra extensions to improve real-time performance. So they wanted to have timing of that. So for receiving, we implemented the SO timestamp SOC option in NuttX. So every CAN frame we get a timestamp as well. And something we did extra in NuttX, which the Linux doesn't have, is we also want to have some kind of a TX deadline option. So if we transmit the frame, we set a deadline, and if the CAN controller cannot transmit this frame during that deadline, we remove it from our internal buffer. And this is to ensure, especially from a safety perspective, is if there is too much traffic going on or the cable is failing, you don't want to buffer up all your frames and flush them out, and then you kind of start with the new relevant frames. So this is mainly for safety requirements, and also just keep your system real time. And if we cannot process this data, we don't want to end up in some kind of deadlock. So to implement these extensions, we still want to stay portable. We still want to stay compliant. So we implemented the control messages, which is also a POSIX standard. So NuttX still didn't support control messages, so we extended the receive message and send message function, so we can have this express timestamping information through C-message control messages. Fortunately for me, it was already partially implemented. So in the sys socket we already had it, but the functions were not using it. So we've implemented that part, and now you can enable control messages. For now, only SocketCAN supports it, but I think in the future it will be very interesting to add control message support to the Ethernet layer as well. Since nowadays you also have time-sensitive networking, and we see in microcontrollers that there is more often an Ethernet controller, and of course you're going to have the same timing requirements. So now we have SocketCAN in NuttX, and then the question is, okay, let's port a existing SocketCAN application to NuttX, and this was quite easy. So in this use case, we wanted to port the Linux CANutils candump tool to NuttX, and we only have to change the headers from the Linux headers to the NuttX headers. And in this case, we had to disable some signals which are not that useful in a NuttX, so it also doesn't support. And so ideally, you only have to change 2 lines or even more, but the effort is very low, and you already have this well-established application into NuttX. So this is the SocketCAN candump demo. So this is running on our UCAN S32K146 board. So we have enabled SocketCAN, we have enabled the network stack. So we get our network utilities already. So this is the interface config. We can see we have 2 CAN controllers. We can turn CAN controllers off. We can turn them on. We have nice handlers that we can save power and stop the handlers. This is the port of the candump utility. Everything is working. We have all these extras. And this is just an example where we can just have a candump on this CAN 0, and we see the data coming through. So in the CANutils, we also have the CAN send demo. I think it was also nice to showcase. So again, we have our NuttX cell. We have enabled the CAN send tool, and we have to ensure that our interface is up. We can send our CAN frames, just the same format. And here at the bottom, we see that we receive data. We also support CANFD. Yes, and here we can see that we can receive this data. So both candump and CAN send are in the NuttX apps. So if people enable this and they want to debug and test, they can easily use these 2 links. So where do I use NuttX and SocketCAN for? So I'm part of the mobile robotics team, currently focusing on reliable communication and functional safety. And we're looking at CAN. We want to encourage people to use CAN instead of point-to-point UART or I2C on long wires, where CAN is designed for these problems. And you have to think about ease of use and usability. Furthermore, especially in the drone industry, in the PX4 community, they are working with UAV CAN, And right now I'm working on to implement UAV-CAN on top of SocketCAN for using this piece for autopilot. Furthermore, my colleagues Yari and Sis also worked with SocketCAN and UAV-CAN, where they made a smart battery management system that runs NuttX and also uses CAN, UAV-CAN to report the battery status to the CAN bus. And they will present this tomorrow at 17 GMT. Conclusion, well, SocketCAN prevents developer a nice standard POSIX based API to send, receive data on the CAN bus independent from the CAN hardware. So right now in NuttX, we support SocketCAN for the S32K family and for the Kinetis family. In the future, we also want to extend this support to the IMX RT family, and also for my personal project, I've ported to the LPC 7068. So I'm also working on to make a nice spec to get that also upstream. If you want to add SocketCAN to your favorite microcontroller, I've nicely written down the instructions into the NuttX exporting guide, and you can find it this chapter. And if you have any questions, feel free to ask me. Thank you.
Great presentation. Congratulations, Peter.
Hi.
Are you listening to me?
Yes.
Right. So let's go into check for questions from the attendees. So Alan is asking you, did you measure the overhead and or increase of memory of the SocketCAN compared to the native NuttX CAN driver?
I didn't do it for NuttX. So I had this problem where we didn't have a CAN driver for NuttX through the character device for our hardware. What I did do is I used the Zephyr RTOS, which already had support for SocketCAN, and we looked into the latency numbers of that. Fortunately, I don't have them right now, and at least I can say our latency is better than their SocketCAN implementation, but I don't really have the hard numbers. I can look them up for you, but I've measured eventually the latency we have, but I cannot really compare them to the original NuttX.
All right. Let me see if there is another question. Here I have a Brandon question. What are some debugging features that you would find helpful for these types of real-time applications? Completes. In Linux, BSG, there are powerful hooks with BPF.
Okay, I'm kind of back to basics. I'm just mostly using GPO toggles, and I'm using a logic analyzer to do real-time tracing, because it's a balancing act where you enable extra things which also interfere. And then, of course, Linux, it's a bit easier to do that. What I really would like to have to get is to get multi-threading. I mean, in your debugger, get the multiple tasks working, so you can see which tasks are running, especially if you have some memory corruption problem going on. Then those things are right now kind of hard to debug. So.
All right. Gregory says, thanks, Peter. That was a long, painful effort to get that in place. Get to see it come to fruition.
Yeah, it took some time. Luckily, I had enough time to get all the bugs out. So I guess in that regard, it's quite stable for now, and we're working hard on it. So we're working hard to get a nice, stable API for it.
It's great to see that when we create a standard, we make things easier to others, but it takes really effort when we have to do it.
Yeah. I think when I started it sounded kind of easy, but eventually when you dive deep into it, then yeah, you have to learn a lot. I learned a lot also out of it, so that was very nice.
So let me check it here. Igalaway I don't know how to pronounce it, Galloway, it just says, not mentioned, but one of our NXP colleagues also ported CAN SL to the UCAN S32K146, so it can also be used as a debug adapter into a CAN bus or on a laptop or PC.
Yes, indeed. So one of my colleagues just showcased if we have SocketCAN and we already have our character device POSIX interfaces, you could write in 200 lines, you could implement this SLCAN protocol, and you can convert a NuttX-based device into a CAN sniffer, which is nice because these things are pretty expensive. And it
Yes.
helps with debugging. So we're looking in that if we can maybe make that open source, and but those things are nice to have. Yes.
So I would thank you very much once again. Congratulations for all of your work.